This is an early concept drawing of the American Space Station, with 6 modules linked to the center core module. These modules include life science, crew habitat, materials processing, power generation, and storage. This is an early design concept of the International Space Station, which will contain a power solar generating station. This is an early concept design of the space station. In this concept, there are only 3 U.S. modules with 2 solar arrays. This is an early concept drawing of the International Space Station. The 16 solar panels can be seen in the foreground, along with the space shuttle docked in the lower right. In this low-budget concept of the space station, there are only 3 crew modules, along with future expansion capabilities. One of the main advantages of the International Space Station will be servicing spacecraft before long-duration exploration missions such as a Mars trip. This is an early concept utilizing the space shuttle's external tank for a living habitat, life science, and Earth observation. This picture is a model of the U.S. space station, a low-budget concept containing 6 modules and propellant storage capability. In this concept painting, the American Space Station is slightly larger, with science, crew habitat, and power generating capabilities. This image shows the International Space Station's Canadian arm working on the Hubble Space Telescope during a routine servicing mission. This early concept of the American Space Station depicts large solar arrays and 3 crew modules. These modules include life science, crew habitat, and long-duration storage and material processing. In this painting, the fully constructed International Space Station can be seen in high Earth orbit. Presently, the International Space Station is scheduled for completion in the year 2005. In this concept drawing, an astronaut is shown doing an EVA, performing routine daily maintenance on the space station. This is an early concept drawing of the American Space Station. Please note the large satellite-type antenna in the center of the picture. In this concept, this antenna would beam down energy collected by the solar panels to be used on Earth. This is the current design model of the International Space Station. Please note the 16 solar array panels mounted on the truss structure. At the bottom are the crew habitat, laboratory, and science modules, as well as docking ports for the International Space Station. In this concept drawing, a boom construction machine can be seen. This machine will be designed to build the truss system, which will house the solar panels and link the crew modules and the space station together. This picture is of two astronauts conducting an EVA during the early construction phase of the International Space Station. This early concept design of the International Space Station depicts 6 crew modules in a large truss structure system, along with radiators to vent heat generated by the space station. In this cutaway view of the International Space Station, crewmen can be seen conducting experiments in a shirt-sleeve environment. Please note the truss system, which is the foundation for building the International Space Station. This painting depicts an early concept of the space station in high orbit during the early construction phases. A mock-up of the International Space Station crew module can be seen in this picture. Note the cylindrical shape and functionality. Robots will be a vital factor in maintaining the International Space Station. This is an early concept of an International Space Station maintenance robot. In this picture, one of the International Space Station laboratories can be seen. Please note various technicians working on science packages in a shirt-sleeve environment. This is a concept painting of the American Space Station. Please note the access nodules in the foreground. This will provide expansion as well as space shuttle docking capabilities. This is an early concept picture of the International Space Station containing 6 modules consisting of crew habitat, science, storage, and power generation.
The first station element to be launched is the FGB, a Russian acronym for Functional Cargo Block. About 2 weeks after the FGB is launched, the Space Shuttle Endeavour lifts off from the Kennedy Space Center in Florida, carrying the first U.S.-built station component, a connecting module called Node 1. The node will be attached to the FGB by Endeavour's astronauts, and it will become a central connecting point for future U.S. station modules. Russia will launch the next major element of the station in December 1998, the service module, the first fully Russian contribution. The stage, called an interim control module, could be launched on the second Space Shuttle assembly mission, also planned for December 1998 to carry internal supplies and logistical equipment. Or if not needed, it could be kept at the ready throughout the assembly to be used in case of an in-flight engine failure or other station problem. Only a few weeks after the service module's launch, the Space Shuttle Atlantis launches on the third assembly mission, carrying what will become the anchor point for the 100-yard-long girder-like truss. Along with that integrated truss structure, Atlantis will carry a third mating adapter, a dish antenna to soon provide high-rate communications, and control moment gyroscopes that eventually will maintain the station's orientation without using thruster jets. During the spring of 1999, 3 more shuttles visit, attaching the first U.S. solar panels, a U.S. laboratory, and a Canadian mechanical arm. By year's end, the station is ready for its first utilization flight, carrying early research work aloft in January 2000. 3-person crews permanently inhabit the station, rotating tours of duty 3 to 4 times a year. More solar panels are added, power increases, and research work on the station accelerates. In 2001, a Japanese laboratory is launched, increasing scientific capability. In 2002, a U.S. habitation module launches, expanding the living quarters to accommodate up to 7 crew members. Later, 2 Russian laboratories and a European laboratory join the station. Finally, in 2003, the completed International Station begins at least a decade of operations.
The space station will benefit the launch and recovery phases of future solar system exploration missions. Module launch systems used to launch the separate pieces of the module could be assembled easily at the station to obtain better gravitational escape performance. Recovery of return samples would provide a means for zero-gravity laboratory studies and provide major assistance in areas such as quarantine and thermal and physical protection of samples during re-entry. The station should also provide the first opportunity for extended work with animals, plants, and experimental equipment in weightlessness. Plans to capitalize on that opportunity include the development of a module to support studies of changes in physiological functions such as calcium excretion and adaptation to increasing lengths of exposure to weightlessness. This module habitat will also allow the study of the use of artificial gravity and of the possible effects of weightlessness. Because of these long-term needs, the station must not only be designed for in-orbit maintenance, but also be able to operate independently of the ground as much as possible. Ideally, NASA sees the station as completely autonomous, except for resupply of personnel and materials. It is intended that there be no need for full-time monitoring of the usual subsystem status, detailed crew work scheduling, or crew health check assessments by teams of engineers, scientists, and Earth-based mission controllers. Computers would ideally do most of the station's routine monitoring tasks. As former NASA Administrator Dr. Fletcher said in a speech to the space community, "A space station is the next step in NASA's and this country's future plans. The space station will be the first step in a highway to space." The International Space Station has been scaled down due to increasing project costs. The original plan NASA visualized was a station estimated at a total of $8 billion. However, agency officials soon revised this estimate to $13 billion, along with another $1.5 billion for engineering ground support. The present design is a compromise. This bare-bones station will only require the $8 billion initially proposed. NASA has, in turn, requested bidding contractors to present ideas for lowering their costs. NASA officials believe that erecting this more modest version will cut costs and that the station should be gradually developed over the coming years. This present attitude is closer in strategy to that of many prominent space scientists who fear a more expensive station would be a financial burden and would only serve to threaten investment in other space projects. Some of the financial burden will be absorbed through international participation. In the same State of the Union address in which he called for a permanently manned space station, President Reagan also invited allies of the United States to participate in the development and use of such a station. In keeping with Reagan's offer, several countries will join America in assembling the International Space Station, or ISS. The 14-nation European Space Agency has agreed to supply a $2 billion laboratory to be called Columbus. Japan has pledged a $1 billion laboratory to be attached to the central station, and Russia will supply the core module, along with crew transportation and crew escape spacecraft, the Soyuz.
For years, humankind has dreamed of a space station, a floating outpost above the Earth where people of many nationalities would live and work in the weightlessness of space. That dream is now becoming a reality with the International Space Station. No longer just an idea or a blueprint, the International Space Station is moving from the factory floor to the launch pad. Around the globe, pieces of the station are nearing completion, and international astronauts are being trained for the first missions. Designed to be a cutting-edge laboratory in orbit, the station will be the largest spacecraft ever built, with a wingspan longer than a football field and a mass of almost 1 million pounds. The completed station will include 6 state-of-the-art laboratories, where research is hoped to lead to medical advances, better computers, new industrial materials, and fundamental discoveries in basic sciences such as physics and chemistry. The station will serve as an outpost where international crews will study the Earth and, through their research, pave the way for future journeys into the solar system. The International Space Station is led by the U.S. in conjunction with 5 space agencies representing 14 countries. Elements of the station are taking shape in factories worldwide, cities coast to coast in the United States, in Russia, Canada, Japan, Italy, Germany, and throughout Europe. Constructed in orbit, the station will require 45 different flights using the space shuttle and 2 types of Russian rockets to launch components.
In his January 1984 State of the Union address, American President Ronald Reagan issued a directive to NASA to develop a permanently manned space station by the late 1990s. 3 years earlier, NASA had formed the Space Station Technology Steering Committee to assess the technological needs for a space station and to produce a project definition called for by the Herth Report of 1981. In 1982, under the protection of the Space Station Task Force, this amalgam of engineering, scientific, financial, and administrative experts from each section of the agency conducted a 2-year study to clarify the goals for the proposed space station. These goals are to establish the means for a permanent and productive presence of people in space, to establish routine, continuous, and efficient use of space for science applications, technology development, and operations, to further develop the commercial use of space, to develop and exploit the synergistic effects of the man-machine combination in space, to provide essential system elements and operations practices for an integrated continuing national space capability, to stimulate the mutual benefits traditionally derived from cooperation in space with allies and friends, to reduce the cost and complexity of living in and using space, to be a major contributor to United States leadership in space in the 1990s and beyond, to ensure that the elements of the space station are compatible with and can interface with space elements of the operational space transportation system, to motivate future scientists and technologists, and provide leadership in furthering their education.
Soyuz docking port. Soyuz docking port. Russian module. Russian module. Observation module. Observation module. Observation module. U.S. Laboratory Module. U.S. Laboratory Module. Cruise quarters. Cruise quarters. Docking port. Japanese Laboratory Module. Observation Module. Observation Module. Japanese Laboratory Module. European Laboratory Module. European Laboratory. Docking port. Cruise quarters. Observation Module. Russian Module. Docking port.